Okay, so again, welcome to Princeton Club of Japan. We are pleased to host an event about quantum computing by Professor Andrew Houck. Andrew is a professor of electrical and computer engineering at Princeton. And he is an accomplished Princetonian who completed his undergraduate studies in electrical engineering back in 2000. After a PhD at Harvard and postdoc at Yale, he has been back at Princeton as professor. He was part of the team that discovered the superconducting Transmon Qubit, which is one of the key technologies being used right now in the most powerful quantum computers, such as those at Google and IBM. Professor Houck is also director at C2QA at Brookhaven National Laboratories, spearheading quantum computing efforts at national and international level. Quantum computing is one of the biggest revolutions in computing since digital computers were first invented. Computers have been increasing in performance and decreasing in size and power consumption for almost a century, but we are beginning to see the limits recently due to the failure or almost failure of Moore's law. Furthermore, there are problems which are known to be fundamentally intractable for traditional computers. The world-renowned physicist Richard Feynman, however, foresaw a revolutionary way to get around this problem using the laws of quantum mechanics. This is what led to the development of quantum computers, one of the hottest new technologies of today. So without further ado, we'd like to give a warm welcome to Professor Andrew Houck.
Thanks, Hede. It's great to be here. You've disabled screen sharing though.
So, whoops. Oh, sorry. I need to, hold on. I need to make you co-host. There we go. There we go.
Great. Now I have all the power. Okay. Let me just do this. Great. So I'm going to talk sort of, everybody can see my slide, yes. I'm going to talk more broadly about quantum computing and quantum technologies and what it is, and the work going on at Princeton in this space, which is I think quite substantial and growing. And so it's a very exciting time both in the field and at Princeton. When we talk about quantum computing and quantum technology in general, we're really talking about what we refer to as the second quantum revolution, which begs the question, what's the first quantum revolution? So quantum mechanics is the field of physics that arose initially from studying the atomic world, from studying very small, simple systems and trying to understand how the world works at that level. And it turns out that it's quite different than anything that we sort of know today, or anything that at least you have a good intuition for today. And when the sort of pioneers of quantum mechanics in the early 1900s were studying quantum mechanics, there was no technology in sight. They were just sort of asking basic questions about how the world works. But it gave rise to these this new understanding of materials. And this new understanding allowed scientists 50 years later to start to actually make new kinds of devices. And in particular, I show two important devices here that you wouldn't be able to build if you didn't know quantum mechanics. And this is the first transistor ever made on the left, and the first laser on the right. Now, these are quantum devices in that if you don't know quantum mechanics, you can't understand the band structure of silicon that you need in order to build a transistor, or the energy levels of atoms that you need in order to build a laser. And so if you don't know quantum mechanics, you could never build these devices. But once you've built them, they operate in a very, very, very classical way. That is, you don't need quantum mechanics to understand how a transistor works. You can think of it as a switch that's on or off. It can encode a 0 or a 1. Laser shines, a beam of coherent white, but the light that comes out looks like a sine wave. It's sort of the most simple kind of light. And so the outputs of these devices are very, very classical things. I like to show these pictures because the technology here is clearly technology that is barely technology. These are lab experiments. No one would believe that we would be producing, I think that's like 1 trillion transistors second, or it's even more than that right now, across the world, and have lasers that are absolutely microscopic and have enormous amounts of power. I'm able to give a talk to you while you are on the other side of the world right now, because I have a computer that's full of these transistors, and it's connected to basically a glass tube that has a bunch of lasers that are firing repeatedly, and that allows my talk to appear on the opposite side of the world. That's all because of quantum mechanics and what we call the first quantum revolution. But similar to the first quantum revolution, I think starting maybe 40 years ago, scientists started asking thought questions. They weren't really thinking of it as a technology, but just sort of hypotheticals. Suppose we didn't just have to understand quantum mechanics as it relates to materials, but suppose we could actually have the outputs of these devices be quantum mechanical. What kinds of technology would be possible then? Could we do anything that we can't do now, or is sort of the sum total of what we have from transistors and lasers, or is that it? And it's that kind of hypothetical thinking that led to what we call the second quantum revolution. So I think in order to go too much further, I need to introduce the three big principles of quantum mechanics that give rise to the weirdness that is sort of fun to talk about from a fundamental science level, and also the sort of new rules and new tools that you have at your disposal when you're trying to build technology. Okay, so three quantum principles. The first is the principle of superposition. This is often sort of referred to as Schrödinger's cat. And what this is that in quantum mechanics, an object can be in more than one state at the same time. And so we know this to be true. If you have an atom, it could be in its ground state, it could be in its excited state, that seems reasonable, but it can also be in a superposition of its ground and excited state. It can be both in its 0 and its 1 state at the same time. And you have to specify, if you're sort of trying to describe the system, not just is it 0 or is it 1, but how 0 is it really and how 1 is it really? This feels really counterintuitive, of course, because when you see objects in real life, they're usually one thing or another, and Schrödinger sort of put it as a hypothetical. If you see a cat, it's alive or dead. It's not both. But in quantum mechanics, you're actually allowed to have both. That's weird. But you could ask, why don't you ever see something walking around that's alive and dead? And that's because of the third thing. I switched the order. The third thing here that says that measurement fundamentally changes the system. So if you see a cat and you look at the cat, that's a measurement. And when you measure it, it destroys any possible superposition. It puts the system into one state or the other. This often goes by the name of the Heisenberg uncertainty principle. So the Heisenberg uncertainty principle says that there's certain pairs of things that you can't know about the universe at the same time. For a particle, you can't know its position and speed at the same time. And the reason is because measurement changes the system. It's not because, oh, you can't measure accurately enough or anything like that. It's a deep and fundamental thing. And what it's actually saying is that when you measure something, you sort of force the system to be in a state that corresponds to what you're measuring. So if I measure a cat that's both alive and dead, then it forces the cat to be either alive or dead. But not everything, not every measurement is compatible. That is, if I measure where a particle is, it forces it to be where I measured it. If I measure how fast a particle is moving, it forces it to be moving how fast it was, like I measured it to be moving. But it turns out that you can't have a well-defined position and a well-defined speed at the same time. Those states just are not compatible. They're superpositions of each other. And so once you measure one, you sort of destroy the other. The third principle, which I've listed in the middle for a reason I don't remember, but I thought it was a good idea last night when I was throwing this talk together, is this principle of entanglement. This is what Einstein referred to as spooky action at a distance. And this says that if that if you have two objects, they can become correlated in a deep and fundamental way. And not just that they can become correlated, but these superposition states can become correlated. So for instance, I could have a state where I have two cats, and I could put them in a superposition state where both cats are alive or both cats are dead. This isn't to say that I don't know the state of these cats. That's a very different thing. It's actually that they're both at the same time. But I don't allow the superposition where one is alive and one is dead. So they're correlated. Then my cats, I can send one of them to the opposite side of the universe, and there's still that correlation persists even regardless of how far apart they are. And then if I make a measurement on one, that collapses the whole system. So if I look at one cat who's alive, I know that the other cat on the opposite side of the universe is also alive. So these correlations persist across distances, and a measurement on one affects the whole system. What this means is a system can't be described by its individual parts, but you have to describe the whole system as a collective. These are really the three things. If you have these three laws, you can build a mathematical framework about them to actually describe what's going on in quantum physics, at least as far as everything we need to know for quantum computing is concerned. It turns out that each of these principles maps pretty closely onto an actual technology. So we think about the superposition, the principle of superposition. It says that an object can be in more than one state at the same time. That is something that actually gives us real power when we try and think about computing, because it means that we can put the input of some algorithm not into sort of one input. I want to test this thing or I want to test that thing, but you can put the input of a large complicated computing system into a superposition of all possible inputs. And this gives you an enormous amount of power when you do computing. Now, it's not quite as simple as you can do all your problems at the same time, but it does give you an enormous amount of power. And that allows you to solve seemingly impossible problems. We know how to do them in cryptography, possibly. There's definitely some things in optimization, possibly in finance, possibly in drug discovery, because it involves so much simulation of chemical compounds. Entanglement, this spooky action at a distance, allows us to have absolutely new unprecedented levels of sensitivity in sensors. So we can probe materials and biological systems at the nanoscale with unprecedented sensitivity and resolution. We can use quantum sensors to build inertial navigation units for GPS-denied navigation. It allows us to build sensors that can measure quantities in the universe much more carefully than we thought possible with only classical systems. And measurement is useful in terms out for communication. The fact that measuring a system fundamentally changes the system means that if you are trying to do secure remote communication, you can actually have provably secure communications where you're not relying on some math problem being hard to solve, but you can detect the presence of an eavesdropper, somebody trying to steal your information, because their measurements fundamentally change the information that you're trying to communicate. And so it allows you to give provably secure communications based on physical guarantees, based on the laws of physics as we know them being true. And these are the areas where we say that quantum is revolutionizing technology, computing, sensing, and communication, which it turns out is an enormous fraction of space in technology. And so this is what we're trying to realize. I'm going to give you just one quick example of the kinds of things that go on when you actually do this for quantum states, and one example of a quantum computing algorithm in a very hand-wavy form, because this is not that long of a talk, and I want to keep it fairly non-technical. But you can see sort of the power of quantum computers in particular when you think about quantum states. So if I have a 3-bit computer, it can't really represent a lot of information, right? It's 3 bits. I can represent the numbers from 0 through 7. in binary that you see here. And if I have 3 bits, you put your computer in one of these 7 states and it can represent a number between 0 and 7. If I want to describe this, if it were a quantum computer though, I can't just have my 3 bits in these 3 numbers. I actually need 8 numbers that tell me more or less the probability that I'm in each of these states. It's even more complicated than that. These are what we call amplitudes. They're complex numbers. But from an overview perspective, I need 8 numbers just to describe the state of a simple 3-bit system, because I need to tell you, what is the probability that this is 0, and what is the probability that this is 1, and what is the probability it's 2, and what's the probability it's 3. And so I can write a quantum state with these 8 numbers that describe the overall state of the system. Now, as I add more and more bits, it takes 2 to the n numbers to describe the state of the system. And so the complexity of a quantum computer grows absolutely enormously. My favorite example of this growth of complexity is 800. So an 800-bit quantum computer, that's, classically, if I have 800 bits, that's basically a text message. That's not very many characters. In quantum mechanics, I need 2 to the 800 numbers to describe an 800-bit quantum state, because I need to tell you how likely it is to be in the 0 state, and how likely it is to be in the 1 state, all the way up through how likely it is to be in the 2 to the 800 state. And so if you have 800 bits in a classical computer, it's a text message. If I have 800 bits in a quantum computer, I need 2 to the 800 numbers to describe it. And the reason I like 2 to the 800 is that it's the number of atoms in the universe. So if you were to try and write down the state of an 800-bit quantum system, you would actually need to write a number on every atom in the universe, which shows you how quickly the complexity of these quantum systems grows. Now, that doesn't necessarily mean that you can do something useful with them, but it does say that describing a quantum system becomes enormously complex very, very quickly. And this was the real initial inspiration for thinking about quantum computing. It was this idea that if I'm trying to describe a quantum system on a classical computer, it just takes an enormous number of numbers to actually describe the state of that system, and it becomes practically impossible. And so if you want to try and have any hope of describing a quantum system, then you need a quantum computer, something that sort of is written natively in some kind of quantum language and allows you to describe things quantum mechanically, because otherwise you just don't have any hope. So we can use this complexity to our advantage. And my very favorite example problem is a very small version of what's called Grover's search algorithm, which is I'm thinking of a number between 0 and 3, and I ask you to guess it. Now, this is obviously not a deep and meaningful problem, but classically it takes, as it turns out, it takes 2 1/4 guesses on average to get this problem right. So you have a 1 in 4 chance of getting it on your first guess. You have a 1 in 4 chance of getting it on your second guess. And then as long as you're not doing something not very smart and guessing the same number multiple times in a row, it doesn't matter what you guess on your third guess. After your third guess, you always know the number. You don't need to make the fourth guess, because if you got it wrong 3 times, the fourth thing is the right answer. So it takes 2 1/4 guesses on average. A quantum computer is able to get the number every time in 1 guess. So it knows the number every time after 1 single guess. And this is what we mean by it can solve seemingly impossible problems. It can use fewer queries to a database. It can use fewer steps in an algorithm than we think is classically possible, or even that intuitively makes sense. And the way you do it is, instead of guessing 0, 1, 2, or 3, you guess 0, 1, 2, and 3 at the same time, because your computer can be in a superposition. And what you get back is 0, no, 1, yes, 2, no, 3, no. You get back this state that has literally the answer to every question you could ever ask. And this, I feel like, is amazing and full of false promise, because it feels like this has everything you could ever want in it. And it is in fact true, somehow embedded in these numbers that describe the probabilities of what we measure. It actually has every piece of information you could ever want in there. But the world doesn't work like that. We can't get access directly to these quantum states. What we can do is measure these states and get outcomes based on probabilities. And if I take this state and I look at it, I have an equal superposition of 0 no, 1 yes, 2 no, and 3 no. And if I look at it, then I get one of these 4 things at random, which turns out to be even worse than the classical thing you could do, because what it means is you basically just get one guess, but you don't even have the ability to control what guess you get. You just get one of these 4 possibilities at random. And so what you do, and this is really the kinds of things that gives quantum mechanics its power, is you do something that looks like an interference experiment. So I can sort of take this piece of information, 0 no, 1 yes, this superposition state, and I can run it through what's basically like an interferometer. If you're sort of familiar with any kind of optical interferometer, you sort of take this state and you kind of split it into 2 pieces, and then you try and recombine it. And this splitting is a common kind of quantum gate. And what you can do is you can arrange it so that you get a little bit of a phase shift. If your state is, for instance, a no or a yes. And so if you do that, you get this sort of 0 no, 1 yes, 2 no, 3 no, but you can turn the sort of amplitudes for the no states negative. And when you try and recombine it, the only thing that's left over is the answer you want. And so it's this kind of interference effect that you can use to get the right answer you want, but it relies on the fact that you're looking at a global property of a complex system. So these are the places where quantum computing tends to be valued, is not when you want to get sort of the answer to a whole bunch of questions. It's when there's sort of a needle in a haystack and you're trying to find some piece of information that exists that requires computing on a huge fraction of your space and then trying to extract one slight bit of information. I'm being very vague about how this interference process works. There's a sort of longer version of this talk with a lot more technical detail where we can get into it, but it's a little much for this talk. I'll also point out that this guessing game only works in one guess. For this very simple problem where there's only 4 numbers. It turns out that as you build it larger and larger systems, you can use this to get a real advantage, but you need square root of n guesses if you're guessing a number from 1 to n. So it's better than your sort of classical computing, but it's not one guess for larger systems. This tells us sort of a general algorithmic approach. There's certain problems that we can solve in fewer steps than the classical counterpart, and sometimes exponentially fewer. It's an algorithmic speed up. When classical computers have gotten better over the years, they've gotten better because they do each step of a problem faster. As processing speeds improve, just the number of the steps get faster and faster. But they don't really change the number of steps you need to do. Quantum computers are probably going to be substantially slower in terms of the clock speed than classical computers, but they just need fewer steps. They're changing the algorithmic complexity rather than the speed of the processor. Almost every algorithm starts with a massive superposition of all possible input states. You're basically exploring the answer to every possible question you could ever ask your algorithm. And then usually what you need to do is some careful manipulation of your state in order to get the one piece of information you want. And usually quantum computers are effective at problems where you're trying to get a sort of narrow bit of output out that requires knowledge of this full parameter space, like brute force search or finding the period of something, or some kinds of optimization problems. These are things that require exploring parameter space, but then only extracting a small piece of information from that large exploration. And that's really where quantum computers are good. Okay, I wanted to finish by talking a little about I want to talk about how to build quantum computers, and I want to talk a little bit about what's going on at Princeton. So I'd say, why don't we have quantum computers? People have been working on this for a while now. Like we should be done. And I think there's really a fundamental tension in quantum computing that makes it a really hard problem. And it's this tension between having a system that's connected and isolated. So I said in the beginning of the talk that when you measure a system, it fundamentally changes in output. A person doesn't have to be involved in that measurement. Really, if anything in the universe interacts with a system in a way that extracts information or sort of could glean some information, that's effectively a measurement. And so if you want a system to remain in these superposition states for a very long time, which you need to have happen for quantum computing, then you need them to be very isolated from the world. And so if you take a system and you really do an amazing job at isolating it, you can have these superposition states persist for incredibly long times, which is all well and good. But then you remember that when you're doing quantum computing, you actually want to manipulate the system. You actually want to get in there and change these states on demand, right? That's what an algorithm is. It's, you know, flipping zeros to ones and all the rest. And it turns out that if you have a system that is incredibly well isolated from the world, it's also quite well isolated from you, and you can't manipulate the system very quickly or very well. You could, on the flip side, start with something that's more well connected. And that gives you fast input and fast output and fast operations. It allows you to do everything quickly, but it also allows sort of the universe to do everything quickly. And these superposition states are fragile and decay. And so there's sort of different starting points in quantum computing. There's sort of circuit-based approaches, which is what my research is on. We actually take superconducting metal patterned on sort of conventional microelectronic techniques, and that can encode quantum information. These circuits are physically, you know, fairly large. They can be manipulated with electric and magnetic fields, similar to normal circuits. So it allows you to do fast operations, but what we call the coherence time, the lifetime of a quantum state is short. Similarly, you could start with atoms and ions, which are incredibly small and tend to be well isolated from things around them. And if you start with atoms and ions, you have these low error rates and long memory times, but operations tend to be slow. And in most quantum systems right now, whether it's atoms or ions or circuits, the ratio of how fast you can do something to how long the information lives is about the same. And I think what's happened over the last 20 years is this sort of march towards the other direction. So my work starts with circuits, and we try and find ways to isolate the circuit in almost every possible way, except one very, very, very narrow channel, which you can use to do fast operations. The folks who do ion and atom-based quantum computing are trying to sort of find new ways of really quickly controlling these atoms and ions in order to do faster gates. And so, you know, we're sort of starting at one endpoint and finding ways to sort of march towards the other direction. I think this shows the progress in my field of superconducting circuits. So what I've plotted here is the coherence time, how long a superposition state of zeros and ones can live. So the very first superconducting qubit lasted for about a nanosecond. It was invented at NEC in Japan. So go Princeton Club of Japan. And what we've seen is a Moore's law-like growth over the years in how long a superposition of 0 and 1 states can live. And so, you know, these last entries are a little bit misleading in that they're like slightly different kinds of qubits, but certainly from 1999 up to 2013 or so, we saw a 5 order of magnitude improvement. And some of my work recently has started to push this up again. At the same time as we've gotten things to live longer, large tech companies like Google and IBM have gotten into the game and have taken these qubits and worked hard at the scaling problem. How do you not just have one qubit that lasts a long time, but can you make 50 qubits that last a long time? Can you make 100 qubits that last a long time? And these are already complicated enough systems that they can't do anything of use that you can't do on a regular quantum computer. But they're certainly hard to describe what they're doing on a regular classical computer. And so Google famously announced an algorithm that was that they could run on their quantum computer that was incredibly hard to simulate on a classical computer what the quantum computer was doing. And so we can now build complicated enough systems that we can control where you can't really predict exactly what's going to happen on regular computers, at least not without a substantial amount of work. And that's where the field is. So it's at a point where we can do hard things, but not yet useful things. And so we need to build bigger systems still. We need to make the information last longer in order to move into actual useful quantum technology. So what's Princeton's role in this? So I'm, in addition to sort of all of the other things, I'm the director of what's called the Princeton Quantum Initiative, which is an organization that started a few years ago at Princeton that brings together folks from many different departments at Princeton in order to try and tackle these problems in a more cohesive manner. What I think is really fun about this field is that it's incredibly multidisciplinary. And what I think is somewhat unique at Princeton is that we really have absolute strength across the entire stack of quantum information technologies. So starting from materials up through devices, architecture and error correction, packaging, algorithms, all of these things have to come together in order to make quantum computers work. And we have expertise in some way or other at all of these things at Princeton. And what we do in the Quantum Initiative is we try and break sort of traditional departmental boundaries and silos and bring all this together. So I just wanted to give you a preview of some of the things that are going on at Princeton in these areas. So for instance, materials discovery and enhancement. Obviously, if you're building a quantum computer, you have to build it out of materials. In our physics department, we have folks like Ali Yazdani and Zahid Hassan who are building fundamentally new quantum materials, 2D materials that have the potential in 20 or 30 years to have some intrinsic quantum states that are robust against all kinds of error. Bob Cava in the chemistry department, working with me and Natalie De Leon in electrical engineering, have figured out new materials to use for superconducting systems. They give a threefold improvement in the coherence of quantum computer. We are looking at diamond systems. In particular, Natalie De Leon and Jeff Thompson are looking at diamond-based systems. So it turns out that if you have a diamond and you remove a carbon atom from the diamond and you put in a different atom in its place, then you get what's called a color center. It's a defect in the diamond that if you shine a laser on it, it glows of a certain color. These sort of point-like defects in diamond act like atoms, even though they're actually in a solid state system. These allow you to manipulate light, and these are the potential backbone of both quantum sensing systems and also long distance quantum computing systems. And trying to figure out which defects are the right defects to use is a huge materials discovery problem. Once you have the materials, you need to turn them into devices. And we have lots of different people using all kinds of different physical systems at Princeton to look at quantum computers. On the top left, I show a picture of a silicon-based quantum bit. Here you have basically a piece of traditional silicon, and you use some clever, very small metallic gates on top to pull single electrons into little traps. And you can manipulate the spin of those electrons to do quantum computing. This middle experiment is something from my group. It's a superconducting circuit that we used to simulate materials in curved space, kind of like what you might see near a black hole. On the top right, you see work that people have done at Princeton on cold atom based quantum computing and quantum simulation. So each of those little dots you see is a single atom that can be held in a grid of states and moved around. And you can use this to simulate new kinds of materials that might potentially emerge. When you think about architecture and error correction, you have to put these things together in new systems. How do you put them together in new systems? Go on first. How do you put these devices together into systems that can do something actually functional? This is the field of computer architecture, and there are really two people who started thinking about computer architecture in a deep and meaningful sense in the world, basically, before anybody else. One of them is at Princeton. Margaret Martinosi is one of the world's first and premier quantum computing architects, and she's been able to find ways that you can cleverly compile and rearrange things in how IBM and Google and IonQ do their quantum computing to get giant gains in the efficiency of how they use their qubits in their system. And this becomes incredibly important because, as I said, these quantum computers are getting very complex, but they're still only 50 bits or 100 bits in even the most advanced quantum computers. And so making sure you use them absolutely efficiency is what happens in our computer science department, especially in Margaret Martinosi's work. Then there becomes a real packaging and infrastructure and control problem. I showed you that picture at the beginning of the very first transistor, but if you want to build large and complicated systems, you need to build you need to build things that don't look like this. So the top left is a picture of all of the filtering and isolating work that goes on in my group. In order to actually get one of these qubits to work, you need to find a way to make this look more like a real system and less like something that has various things all glued on with various kinds of metal. And so thinking about that matters quite a bit. We want to turn that horrible looking thing I had into this, which is IBM's version of the exact same system. It looks sleeker and nicer, of course, and that's because they're experts in packaging and control. It turns out that at Princeton, we also have Princeton Physics Lab nearby, and they've spent a very long history of doing very large-scale, complicated system development, mostly in the interest of fusion energy, but they're starting to think about quantum problems. And so getting them involved has been incredibly helpful at thinking about this sort of large-scale systems engineering that you need to do in this space. And then finally, we want to think about algorithms and applications, right? Because now we've had for a long time a small handful of applications, but we don't know, they're not necessarily all the applications you can get. And so the question is, what else can a quantum computer do? And can these near-term quantum computers do something that's actually useful and not just hard? And that's really where our computer science and algorithm development is going. Cutting across all of this, of course, is education and training. Princeton is first and foremost a university, and we've pioneered a number of courses in quantum information that have been taught at many of our peer institutions, both in terms of algorithms for quantum computers, what a quantum computer can do. We have quantum algorithm courses that require no knowledge of physics whatsoever and are in fact often a gateway into physics for many of our students. And we have courses on, for instance, how to build all of this technology. We have an enormous quantum center. So the US government takes quantum computing very seriously. Congress enacted the National Quantum Initiative Act, which created $525 million centers to try and bring this technology to fruition. And I'm the director of C2QA. So that is one of these 5 centers. And it's really trying to build a bridge to the quantum era. We have 25 partner institutions bringing together all of this technology. I'm the director. We have thrust leaders at Princeton, and really a substantial component of this is centered at Princeton. I just wanted to flash up in the end. These are all of the faculty now at Princeton, scattered in different departments who have who work in some piece of the quantum space. And so I just wanted to share this to share the excitement and momentum that exists at Princeton in this space. And thank you for listening. So thanks, everybody.